I'm going to look at a topic that I find quite fascinating. I'm going to talk about rate equations and orders of reaction and how that leads on to reaction mechanisms. If I take, for example, this chemical reaction, hydrogen plus iodine forms hydrogen iodide gas. This is totally gaseous. Now, this reaction has been investigated many, many times, and when you do this reaction, you find that the rate is proportional to the concentration of the hydrogen. So if you do the reaction again and double the hydrogen concentration, it goes twice as fast. You get the products twice as quickly. If you do the experiment again and you double the concentration of the iodine, again you find that that doubles the rate of the reaction. So there's a simple proportional relationship. You might be looking at it and thinking, oh, well, I could have told you that. It doesn't always work that simply. This is a sort of predictable example, but the predictions don't always come true. Right, this leads to a rate equation. If we put this together, there's a constant to remove the proportionality. So the rate equation is a constant times the concentration of hydrogen times the concentration of iodine. Now, because there was a simple proportional relationship, we call that first order. If I double that, it doubles the rate. If I triple that, it triples the rate. If I halve it, it halves the rate. Same discussion applies to the iodine here. Again, it's first order. Whatever you do, there's a simple relationship to the rate of the reaction. If you make that 4 times as big, it goes 4 times as fast. Okay, well that was fairly, you probably think, well, I could have guessed that. Let me just take another example here. I'm going to take nitrogen monoxide reacting with oxygen to form nitrogen dioxide. Now that has a rate equation looking like this. Probably better to put the state symbols in to do that properly. In this case, the NO concentration is squared. Now that means second order. The point about that, if you repeat this experiment and you double the concentration of the nitrogen monoxide, it goes 2 squared, in other words, 4 times as fast. If you repeat the experiment and that's 3 times the concentration, it's 3 squared, it'll go 9 times as fast. So whatever you do to the NO concentration, you square it and it has that effect on the rate. Students at this stage will say, why does it do that? Why is it having that relationship? But that's what it does. That's the reality of the chemistry. We have to try and find an explanation for it going on the facts. These are the facts. You can do these reactions over and over again and it doesn't ever change. So we say second order for the nitrogen monoxide, and you'll see this one doesn't have a power there, so that one is first order. Okay? Now, again, you might think, oh, I could have predicted because there was a 2 there and there was a 1 there, but again, it could be misleading. Let me just give you a third example. So propanone, old name acetone, reacts with iodine to form iodopropanone and hydrogen iodide. Now, you can investigate this all day long. By the way, there's an acid catalyst in there. It requires a little bit of acid for that reaction to happen. You can investigate this all day long and you come up with a rate equation, again, which is based on the facts. This is not a theory, this is purely factual. The rate equation is the propanone concentration times the acid catalyst concentration. What do you notice is missing from there? And this is where it gets mysterious, this is where it gets intriguing. In my rate equation, I've got it first order for the propanone, first order for the acid catalyst, but the iodine is missing. Okay? So doubling the concentration of the iodine doesn't make any effect to the rate of the reaction. Tripling the concentration of the iodine doesn't make any effect to the overall rate of the reaction. And you might think, well, that's very, very intriguing. How could that be the case? Well, it is, and you can show this over and over again. This is the rate equation. The rate only depends upon the concentration of the propanone and the acid catalyst. So we say that it is zero order for the iodine. The iodine doesn't have a direct effect on it. So it's zero order for the iodine. Right, what I'm going to do now is give you a little model of how you can rationalise how something could be zero order. You might think, how could a reactant not affect the rate? I'll give a little model and you'll think, yeah, that makes sense. I could see how that would not affect the rate. Right, here's a little simple task, which could be done in any lesson by any teacher, producing a little booklet. I've got 5 pages here, which I started off with these laid down in 5 piles, page 1, 2, 3, 4, 5. To make the little booklet, my job was to take 1 page off each pile. That took a few seconds to do that. The second job was just to shuffle it on the desk, get it nice and tidy. The last job was to put a staple in it like that. Okay, so there are 3 roles there to make the little booklet. The collator, collecting the paper, the shuffler, tidying it up, and then stapling it. Right, so the question I would ask students is, I'm making a pile of booklets for the class. If I have 2 collators, 2 people collecting the piles, the papers off the piles, what effect will that have on the rate of production of my booklet? The answer is it will be twice as fast because I've got 2 people doing it. Why is it twice as fast? Let's think about the shuffling and the stapling job. The shuffling and the stapling job are quick, happen very, very quickly, and we're hanging around waiting for the papers to be collected together. So if I have 2 collators collecting the paper, it will go twice as quick. In that model, you could say that the paper collector was first order. 2 of them, it goes twice as quick. 3 of them, it goes 3 times as quick. So the question I then ask is, if I have 2 shufflers making a tidy pile, if I have 2 of those, will that speed up the rate of the reaction or production of the booklet? And the answer is no, because this person's job only takes a second. I shuffle it and hand it to the stapler. So having 2 shufflers makes no difference. Having 2 staplers, will that make any difference? Not particularly. The rate determining step, as we call it, the rate determining step, the one that holds the whole show up, is the person collecting the sheets. So that person would be first order in my model. The shuffler and the stapler would be 0 order. Their jobs don't significantly affect the rate. The final question I'd ask is, do I need the shuffler? Do I need the stapler to get my product? And the answer is obviously yes. Without those people doing those jobs, I don't get my finished product. So in the reaction we've just looked at, the iodine was like a shuffler or a stapler. It had a quick job in there, but without it, we don't get the final product. So that hopefully that little model explains how we can have 0 order reactants. We need them there, but they're not rate determining. Okay, I think we've got the idea of first, second, and 0 order reactions. Now, when the chemist has discerned those facts which are absolutely objectively correct, you can do the experiments over and over and over again and still get the same results. Those are non-negotiable. The job of the chemist then is to produce a reaction mechanism, which is this is where it gets creative. It's a story, inverted commas, to explain the facts. Okay, so a reaction mechanism is a theory that's made up that is consistent with the rate equation. Right, I'm going to give a few theoretical examples here, but I'm not going to use chemical formulae. I'm just going to use very, very simple letters. These are not real chemical symbols. I'm just using reactant A, reactant B, forming product C. Right, if I did that reaction and I found its rate equation was Ka, concentration of A, the question I'd ask you is, what's the order of the reaction with respect to A? And you would tell me it's first order. Doubling A doubles the rate, tripling A triples the rate, and so on. And what is the order with respect to B? B doesn't feature in the rate equation. It's like the shuffler or the stapler. It's got a quick job. So my mechanism will be in a fast step, something that happens very, very quickly. So the rate determining step, the thing that holds the show up, is the concentration of A. So if I just invent a little mechanism, this is where I'm going to get creative now, little mechanism. I've got A turns into a substance X. This is purely fiction here. We don't worry about what these are. And that is a slow rate determining step. That is what takes the time. A becoming something else. I'm not in the real world here, just bear with me. B's in the reaction. B was like the shuffler and the stapler. It's got to feature. So let's have a second step involving B. So now I've got my X, whatever that was. That reacts with B and forms products in a fast step. Okay, so we quickly finish off the reaction in a tidy fashion like that. So A reacted with B to form C. And X was what we call an intermediate. It was a species, a chemical that formed in the middle of the reaction. And this was the rate determining step. Right, the thing about mechanisms, they have slow and fast steps. And the mechanism must be consistent. It has to fit in with the rate equation. This invention here has to agree with that. Okay, so the slow step involves A and B is involved in a quick step, just bang straight through to the products. I want to show you a more developed example like that. Right, I'm going to show you one more similar example. If I've got an imaginary equation, 2 molecules of A plus B go to C plus D. And I find that the rate equation by experiment, again, you can't argue with this, it is second order for A. So remember, if you double the concentration of A, it will go 4 times as quickly. If you multiply the concentration by 3, it will go 3 squared equals 9 times as quickly. It is second order for A. The question I'd ask you is, what is the order with respect to B then? What is the order with respect to B? These are imaginary molecules. Don't stress about what those are, they're just letters. Right, this molecule B here does not feature in my rate equation. So what is its order? Its order is therefore 0 order. B is 0 order. If I repeat the experiment and change the concentration of B, we won't see an effect on the rate. Okay? We need B to be there so that we can get the products. It has to be there, but it obviously has some quick roll. Right, so we need to invent a little mechanism, a little story that explains that rate equation. This is the master really, and the mechanism is subordinate to it. Right, so a possible mechanism for this would be A plus A going to, this is where you can get inventive. Well, let me just call it A2. It's a sort of doubled up molecule. These need to combine together. And this is a slow step. The slow step is what's in the reactant in the rate equation. A's in the rate equation, so this is a slow step, and this is the rate determining step. This is the one that holds the whole show up, getting A to react. And I've got 2 A's because it's second order. I need A and A again. Another way I could write that equation is A times A. So I need 2 molecules of A in my slow step. That's exactly what I've got there. Your fast step is tidying up the loose ends. You just be a bit creative and just come to a conclusion in an efficient way. So now I've got my little complex molecule A2 there. What should I react that with? So I've got A2. This is, again, an intermediate species, we would call it, intermediate. That's now going to react with B to form products C and D, and that's going to be a fast step. Okay? Now, it's most important that you get your molecule counting correct. Mistakes students can make is they get too creative and then it doesn't tally with that equation over there. So if we just check, I've A and A, 2 A's, and B has formed C and D. Okay, so 2 A's and a B have formed the products there. So the rate determining step just involved species A, reactant A. Okay, so remember that whatever's in the rate equation is in the slow step or steps. You could have 2 slow steps. Whatever is 0 order is in the fast steps, because that's a job that just happens like that. That was the shuffler and the stapler. Okay, so I hope that helps you to understand how the mechanism is derived from the rate equation.